couple of days ago, we were reminded about what happens to a charged particle when it's exposed to an external magnetic field. We know that if that charged particle is moving, let's say to the right through an external magnetic field, it's going to experience a magnetic force pointing downwards toward the bottom of the page. We know that because we use a hand rule for deflection. Our left thumb in the direction of the particle, our fingers in the direction of the field, palm points downward. As it's deflected toward the bottom of the page, it ends up going in a circular path because the direction of the magnetic force always ends up pointing toward one point, toward the center of a circle. Now, if we had two electrons doing exactly the same thing, going towards the right in this magnetic field, then those two electrons would both be deflected downwards and both go in a circular path curving downwards. If we had 3 electrons or 4 electrons, same deal. Everything would happen. It would just be times 4, multiplied by a factor of 4. What happens if I put those electrons inside a wire? Instead of moving through an external magnetic field just in the air, they're moving through an external magnetic field as they go through a wire. Now we have an electric current, right? Electrons flowing through a wire is an electric current. The current that powers your iPhone, the current that powers the clock in your house, the current that powers the television in your house. Electrons moving through a wire. Well, these electrons moving through a wire will still experience a magnetic force downwards, and they do that because the charged particles in the magnetic field don't recognize that there's something that the charged particles are in. A wire, air, whatever, the charged particles are moving through a magnetic field. We'd use the hand rule for deflection again, thumb, fingers, palm points downward, but this time, because they're in this wire, it's kind of like they're in a pipe, okay? You're walking through this big pipe, like this underground water pipe or sewer pipe or something. You're walking through this, okay, and you experience a force in one direction, and you want to go in that direction, but you can't, right? Because you're bound by this pipe that you're in. Well, these electrons are bound by this pipe that they're in as well. They're bound by this wire that they're in. They experience a force downward, but they can't go in a circle because they're inside this wire. So what happens instead is this entire wire ends up being pulled down with the electrons. There ends up being a force on the wire, not just the electrons themselves. The force on each individual electron would be F is equal to QVB, that force that we learned a few days ago. The force on the wire itself would be ILB. Now, just like this equation, F is equal to QVB, the particles must be moving perpendicular to the field. Well, here, the wire must be perpendicular to the field as well. Okay, that's required because, of course, if it's not perpendicular, then the charged particles can't be moving perpendicular to the field. So that's the magnitude of the force on the wire. This is the magnitude of the force on the electrons. The direction of the force on both the wire and the electrons can be found by the hand rule for deflection. Thumb, stretched out fingers, palms point downwards, down toward the bottom of the page in the direction of the force. All right, we had some, sorry, before we take a look at our questions, one more tiny little thing. We occasionally have an issue with this thing here, this I, this electric current, which we defined a couple of days ago as the rate of flow of electric charge. And what a lot of people think when they hear that definition, they think the speed, how fast the electric charges are moving. That's not what it is at all. It's not measured in meters per second, it's measured in coulombs per second. So in other words, it's how many charges are flowing per second. Remember the analogy we used the other day? You're standing on the side of the highway with a radar gun, you're measuring the speed of cars. Okay, if you're standing on the highway with a stopwatch and you're counting the number of cars that go by per second, you're measuring the rate of flow of cars. So what are we doing here with electric current? Since it's the rate of flow of charge, we're not measuring the speed of the charges, we're measuring how many charges are flowing past per second. And of course, the units for that would be coulombs per second, which is equivalent to an amp, an ampere, right? We had a few questions. We had several questions, actually, that you worked on yesterday and ended up having for homework last night. The first step was page 603. Page 603 was just a couple of questions on electric current. How are we with those? Those go okay? Those are pretty straightforward, right? As long as we know the equation and so on. We do have to be careful of something like this. Okay, 1.00 milliseconds is 1.00 times 10 to the minus 3 seconds. All right. What about the questions that we had on page 605? Any issues there? No? All right, well, I'll tell you what. Even though you had no issues, I want to at least set up question number 2. We don't need to finish it off if you guys felt like it was pretty good, but I want to at least set it up just in case there's some of you that are just kind of afraid to raise your hand here. It says a thin conducting wire 0.75 meters long has a mass of 0.06 kilograms. What's the minimum current required to make the wire float in a magnetic field? We had another question like this one other time where it said the minimum current. I don't like that term. Okay, that's not right. The minimum current required to make it float. Okay, in the end, it's not the minimum current, it's the current. If the current is less than that, it won't float. But if the current is more than that, it won't float either. Because if the current is more than that, then the magnetic force upwards ends up being too big, and it ends up rising. Well, I guess you could call that floating, I suppose. Okay, but when I think of float, I think of hovering, right? Maintaining the same position, it's floating. So what are we going to do there? Well, that's the same thing as the word. We saw these words over the last couple of weeks here. Same thing as being suspended. It's the same thing as hovering. It's the same thing as when you see the term maintaining the same position above the earth. Okay, all of those things mean that the upward force, in this case magnetic force upwards, equals the downward force of gravity. So we'd say instead of QVB, like we did in a couple of those other questions, we'd say ILB is equal to M times G. Notice, by the way, on your data sheet, that equation is ILB, but it's a lowercase l. I make it an uppercase L when I'm writing it, only because if I make it a lowercase l, if I make it ILB, what does that look like to you? It looks like a 1, right? And I want you to be able to distinguish between the length of the wire, L, and a 1. When it's typed out on a test or in your notes or whatever, then you can tell a lowercase l is an L, right? But when I'm writing it, you can't. All right, so we just rearrange this and end up solving for current. I is equal to mg over L times B. Good there? All right. And the other thing you had to work on was worksheet number 13. So let's take a look at some answers to worksheet number 13. Yesterday when you guys were doing this, a couple of people asked me about question number 3. Let's bring it up there. Question number 3 says calculate the initial acceleration. Well, first of all, we got grams and centimeters, right, that we got to convert to kilograms and meters. But what do you know about acceleration? In Physics 30, whenever you want to find acceleration, what do you got to find first? Yeah. Find a force. Okay, if it's an acceleration due to an electric field, then find the electric force. If it's an acceleration due to a gravitational field, then find the gravitational force. If it's an acceleration due to a magnetic field, then find a magnetic force. And then set that magnetic force or electric force or gravitational force or whatever force it is equal to what, Jacob? Equal to... Yeah. So you're going to say magnetic force equals m times a, and then rearrange it to solve for acceleration, right? So get a force, and then set that force equal to m times a. So let's do this one here. Let's say the magnetic force here is equal to ILB, which is 0.600 amps times L, 0.20 meters times the magnetic field of 0.500 Tesla. I think that gives me 0.060 newtons. And then we're going to set that force equal to m times a. 0.060 newtons divided by 0.050 kilograms. And what do we end up with that one? 1.2? It's meters per second squared, yeah, because it's acceleration, yeah. The diagram you see up on the board now is a diagram of an electric motor. Remember we said when we introduced Ørsted's discovery, his discovery that was made 197 years ago in 1819, that moving charged particles generate a magnetic field, we said that was probably the most, or certainly one of the most important scientific / technological discoveries in the history of the world. We said that just about every bit of technology that we use today uses that discovery that electricity generates magnetism. Every piece of technology, almost including this one. This is a diagram of an electric motor. This is the electric motor that you might find in a toy car or in a real car. You see electric motors in real cars. Now, there's a Tesla dealership at Chinook Center. Have you guys seen that? That's powered entirely by electricity. Okay, there's an electric motor, or probably more than one electric motor, inside that Tesla car. The mix master, as you're baking cookies, uses an electric motor. Your electric drill uses an electric motor. The ceiling fan in your bedroom uses an electric motor to spin it around. Okay, just about, there's so many applications of electric motors. Just about anything that spins electrically is based on this principle of an electric motor, which is fundamentally based on that discovery of Ørsted that moving charges generate a magnetic field. Let's go through the operation of this electric motor. Not because it's a curriculum objective, right? Just like all those other applications we talk about them because we want you to get a bigger picture and to understand where this applies and to understand how to apply what we've learned, not because you have to know the details of the electric motor. All right, well, let's look at this. We currently have two magnets here, a north and a south, and of course, they're only showing part of the magnets. So it would be another south pole down here, another north pole down here. They're just not relevant to the operation of it here. Okay, that's going to create a magnetic field, and that magnetic field is going to go from north to south like this. Now you also have a battery over here, and you can see the negative terminal of the battery is the short side. It's labeled negative, and then we get the positive side on the other side. You're going to get an electric current that's going to flow clockwise around here from the negative side to the positive side. That's electron current. Okay, if you happen to see a question where it was talking about conventional current, then we'd make it go counterclockwise. Not a big deal. It's just that we'd end up using a right hand for hand rule instead of a left hand for hand rule. We get the same results here. So these electrons end up flowing clockwise around into this little black thing that we call a brush. Okay, that brush is touching but is not connected to this thing that we call a commutator. So in other words, the commutator is free to move, but it still all the time touches this brush. So when the commutator and the brush are oriented like they are right now in the diagram, you get an electric current going through the conducting brush, through the commutator, and it goes around here through this thing that we call an armature going clockwise. Back to the commutator on the other side, back to the brush on the other side, and then back to the battery like this. Make sense? All right, so we get how these electrons go around this circuit, this armature, but it doesn't tell us anything about how this armature spins, how this electric motor will spin around to cause the drill bit to drill into a piece of wood or to cause the mixmaster beaters to beat the cookie dough. So how does that work? Well, we have an electric current right now going through a magnetic field, right? We see that there's the one right here going through the magnetic field that's kind of into the page, and then there's the one right here that's kind of out of the page. We're going to label four corners of this armature so that we can describe a little bit better as to what's going on here. Let's label this one corner 1, corner 2, corner 3, and corner 4. And on a piece of paper that I have that I'm holding in my hand right now, I'm going to do the same thing. I'm going to label this 1, 2, 3, and 4. So you see that it's labeled the same way as the armature on the board is labeled, right? All right, we'll take a look at what's going on here. Take a look at what's going on between position 1 and position 2, or corner 1 and corner 2. You got an electric current that's going into the board. It's negative particles, so we're going to use our left-hand rule for deflection here, since these particles are going perpendicular to a magnetic field into the board. Thumb, fingers point downwards, palm points kind of upwards. You see what I'm doing there? So if this piece of paper is our armature, we'd say thumb, fingers palm points upwards. So there's a magnetic force upwards on wire 1, 2. That's going to cause wire 1, 2 to be pushed upwards. Right, see that? But which way is the magnetic force on wire 3, 4? Well, the current goes around out of the page there, so we'd say thumb in the direction of the particle, fingers in the direction of the magnetic field, again from north to south, palm points downward. So what's going to happen to that wire? It's pushed downward. Wire 1, 2 is pushed upwards, wire 3, 4 is pushed downward. What ends up happening to this armature as a result of that? Yeah, it starts spinning, right? Okay, this side goes up, this side goes down, starts spinning like this. The problem is when it reaches 90 degrees like this, you can see that this little spot on the commutator, call it a split ring commutator sometimes, this little insulating strip on the commutator is now in contact with the brush. So now there's no current going through there. Now the current stops. This is done. That doesn't mean the armature stops, though. The armature has inertia. Okay, there's linear inertia that we always talk about, but there's also rotational inertia. Rotational inertia wants to keep if an object is spinning, an object wants to keep spinning. So it does a little bit. It's forced, wire 1, 2 is forced upward, 3, 4 is forced downward, 90 degrees. The force stops, but it will keep spinning a little bit because of inertia. Now, watch what happens, though. Now, once it's kind of spun around more than 90 degrees, now the positions of the wires have changed. Now, if you look at my paper here, you can see that this is 1, 2, 3, and 4. So the positions have gone from 1, 2, 3, 4 to 4, 3, 2, 1. Do you see that? Well, now let's take a look at the current's flowing again now, right? Clockwise. Let's look at the direction of the force now. We've got electric current once again because the commutator is now in contact with the brush again. Current going clockwise again. But this time the current is going not from 1 to 2 to 3 to 4. The current is going from 4 to 3 to 2 to 1. So though it's still going clockwise, it's actually been reversed in this armature. That's the whole purpose of the split ring commutator, is to actually reverse the current. Even though it's going clockwise, it's still going in the opposite direction of the wire. Watch what happens now, though. Okay, I got my paper flipped over so that my the positions of my armature are reversed like they are on the board here. Thumb in the direction of the particle, fingers field, okay, palm points upward. So now the force on wire 4, 3 is upwards. Remember, it was downwards over here when it was over here. Now it's upwards. The force on wire 2, 1, thumb in the direction of the particle, fingers field, palm points downward. Okay, the force is downward. So whatever section of the wire is on the left-hand side will always experience a force upwards, except when it's oriented like this. It just keeps going, though, when it's oriented like that because of inertia. And this side will always experience a force downwards. What's the net result of that? A force, inertia, a force, inertia, a force, inertia, and so on. What ends up happening to this thing? It spins around, right? That's the armature is what's connected to the drill bit. It's what's connected to the blades on the fan in your house. It's what's connected to the wheels of the Tesla car. It's what's connected to the Mixmaster beaters of the Mixmaster, and so on. Whatever it is that's spinning is connected to the armature. Now, if you've ever used an electric drill or a Mixmaster or something like that, you know that we can change the speed of it, right? We can adjust the speed of it. Or I'll get your questions in just a second. Can you provide me maybe with one way where I could make this thing go faster? Like what could make it go faster? Nick? Yes, good. Stronger magnets. Okay, you got stronger magnetic field. That's going to cause a bigger magnetic force, and that's going to cause this thing to go faster. Okay, so good. Stronger magnets. What else, Gary? Bigger current. Good. If you have more current going through it, then that's going to cause a bigger force, and that's going to cause it to go faster. Anyone else? Yeah. Sorry? Not smaller length. We want bigger length. right? The more length of wire that's exposed to it, it ends up getting more force, ends up being a stronger magnetic force, and therefore goes faster. To get more length, what you'd probably do as opposed to, you know, making wider magnets or whatever, you probably end up looping the wire around here so that you get more length exposed to the magnetic field. Does that make sense? Hey, why is it, here's a quick question, then I'll get yours, okay? Why is it that we care only about that length? Why don't we care about this part or this part? Why is it that only this length and this length are the important ones here? Yep. Yeah, the rest of it is parallel to the magnetic field. What's the value of the magnetic force on this wire right here? 0, because it's parallel to the direction of the magnetic field. Okay, we want the force on these two wires. Or? No, it wouldn't. No, it has to have that because you need to reverse the current there. I mean, there are other designs of motors that you can make work, but with the scenario the way that it's set up here, no. If you just took away that split ring, imagine, or if you did take away that split in the ring there, and this was just all a conductor, what would happen? Well, the electrons would go here, and then they'd say, oh, look, that's an easier path. They just short. That's what we call a short circuit, when electrons will take an easier path, and avoid the path that we wanted to go through. Good question. Yep. Like a jump across there? Well, I suppose some potentially could if you had a big enough potential difference. But the reality is, remember we said, electrons like to take the easier path. So even if you made a really, really high electric current here, so much so that it potentially could jump across that gap, this is still an easier path. Even though that's longer, as long as it's a conductor, that's still an easier path than jumping that gap. So regardless of what the current is, as long as you don't put a bunch of resistance in here, then you'd likely get the electrons going around in there. Okay. Good? Okay, I'd like you to take a look at a few multiple choice questions here today. First two that I want you to do go together. They're multiple choice 77 and 78 in your worksheet book. They go with the information that you see here on photon matter interactions. I'm not going to read this to you right now. I'm going to let you read it. But what I want to point out to you before you do read it is that you're going to read through this description of photon matter interactions, and most of this stuff is going to be completely foreign to you. Most of this stuff you're never going to have heard of before. Most of this stuff you may not even understand once you do read it. What do I always say when that happens? That's context, right? Okay, what does context matter? It doesn't. So what you got to do is boil this down to what really matters, right? Don't panic if it talks about, you know, photon may move an electron out of an atom, and in the process a photon disappears. Whatever a photon is, we haven't even learned what a photon is yet. Don't worry about that stuff, right? Okay? The stuff you need to know to answer this question, you've learned. So if you have other stuff in there that you're confused about, don't panic about that. Just go back to basic principles that you know. All right, I'll give you a few minutes to answer 77 and 78. All right, let's take a look now. It says photon matter interactions. This is when a photon, which, by the way, you don't know this right now. You learn this in your next unit, but well, it doesn't really matter for the context of this question. Just so you know, though, a photon is a tiny little particle of light, a little itty bit of light. When a little bit of light passes through matter, it interacts with the atoms and their electrons. There are 4 important interactions with matter that a photon can undergo. The photon may be scattered by an electron, and in the process lose some energy, transferring momentum and energy to the electron. That's something that we call the Compton effect, and we're going to learn about the Compton effect later on this year, but it's not really relevant to this question. The photon may move an electron out of the atom, and in a process the photon disappears. That's what we call the photoelectric effect, which we're going to learn about in our next unit. But again, not really relevant to the question here. The photon may move an electron to a higher energy state in the atom, and in the process the photon disappears. Okay, that's electron transitions in atoms that we learned about in our last unit, but not really relevant to what we're going to do here. A photon may actually create matter. This is kind of wacky. A photon can create matter. It says the most common process called pair production is the production of an electron and a positron. And you don't know what a positron is, but a positron, if you ever heard of the term antimatter, if you've ever read the book Angels and Demons, talk about antimatter, have you read that book? Watched the movie? Matter, antimatter. We can produce, in Angels and Demons, they talk about when matter and antimatter come together, they annihilate and produce pure energy, which is a tremendous amount of energy. Here it's the opposite effect, right? Here we're actually creating the electron and the proton, the production of an electron and proton. A positron has the same mass of an electron, but the opposite charge. In addition, a massive particle such as an atomic nucleus must gain some of the photon's initial momentum. And this is the diagram that we have here. So here's the photon. It's this little wavy thing here. Hits this atomic nucleus, and this positron and the electron go off like this in different directions. All right. Okay. So we kind of have a grasp as to what's going on here. This stuff we don't really know at all. They don't describe anything, but this one they describe it a little bit better. Let's see what the question says. The curved paths of the particles in the pair production diagram result from the electron and positron moving through a magnetic field. In this diagram, the direction of the magnetic field is going to cause, the direction of the magnetic field is which way? Well, we have two charges in this magnetic field. It's either a magnetic field probably that's into the page or that's out of the page. Which one? Well, pick a particle. If we pick the positron, we're going to use our right hand. Thumb to the right, because that's the way it was initially going, to the right. But then it was deflected upwards, so the palm would point upwards, and the fingers would point into the page. If you wanted to use the electron, they would say our left thumb to the right, palm points downward, because the electron's deflected downwards, fingers would point into the page. So the direction of the magnetic field that would cause both of those to behave the way they do is going to be into the page. How many people got that? Okay, does that make sense for the people that didn't get it? It's kind of just a rearranging of that hand rule, right? 78, during pair production, the speed of the electron or positron can be calculated by measuring the radius of the circular path. What's the speed given by? Well, this is just a derivation of that equation that we've used a bunch of times already, right? mv squared over r equals qvb, but we're solving for v here. So the r goes up, the m goes down, becomes qbr over m. QBR over M, the answer would be A. How many people got that one? That one's a little bit easier, right? Because we've done that a bunch of times. Question number one, we've done that hand rule a bunch of times, but again, it's context, right? All right, I want you to take a look at two more questions, please. This time, question number 80 and 81. The question says a proton with an energy of 894 electron volts travels perpendicular to a magnetic field. We're going to circle that EVs because we know that we're going to have to convert that to what units? If we use it, that is, we're going to convert it to what? Joules, right. We're talking about an energy here, right? What kind of energy would this proton have if it's moving, if it's traveling through a magnetic field? What kind of energy is it? Is it kinetic energy? Is it electric potential? Is it gravitational potential? Is it something else? It's kinetic energy. It's moving. It's kinetic energy. It ends up going in a circular path of radius 3.6 times 10 to the minus 4 meters. So we've got EK, and we've got the radius, and we want to find the speed of the proton. I'll tell you what. If you're like me, when you see this question, then you're going to probably say, for the first time that is, you're probably going to say, oh, wait, I know how to do this. FC equals FM, right? How many people did that? How many people did that to start off? Okay, there's nothing wrong with that. It doesn't get us the answer, okay, but there's nothing wrong with that. The first time I saw this question, and it was a number of years ago that this happened to me, but the first time I saw this, that's exactly what I did. Okay, that's what I went to. It was my go-to thing when I'm talking about a charged particle in a magnetic field with this radius. mv squared over r equals qvb. Cancel out a v. Left with v is equal to qbr over m. Got charge, got, oh wait, we don't know what b is, do we? We know what R is, we know what M is, but we don't know what B is. So we either have to find the magnetic field strength, or we have to find some other way to find the speed. Does anybody have another way to find the speed here? What else? Carrie, go ahead. Yeah, what else applies? Sometimes we overlook the obvious. That's exactly what I did the first time I did this question, or first time I tried this question, is I overlooked the obvious. Okay, I got that. I ended up catching that it was kinetic energy and 1/2 mv squared, but not the first time I looked at it. EK is equal to 1/2 mv squared. You got to rearrange that to solve for V. It becomes 2 EK over M. We got to get kinetic energy, though, in joules. We know that 1 electron volt is 1.6 times 10 to the minus 19 joules, and 894 electron volts equals X joules. So you solve for the energy in joules, plug it in there, solve for speed. I can tell you right now, if I had to guess, I'm going to guess between two possibilities. Which two am I going to eliminate right away? Which two do I know are not the correct answer? The fastest anything can go is 3 times 10 to the 8 meters per second. That's the speed of light. C and D can't be correct. They're way too fast. Okay, you look at A and B. I believe the answer was A when we did the math there. Does anybody have that? Anybody get that? So we do get 4.14 times 10 to the 5 meters per second for the speed. Now we go on to question 81. Look, now we're looking for the strength of the magnetic field. All right, now, look, I wasn't so far off. Nick, when you said FC is equal to FM, you were on the right track as well, right? You just did it a little bit too soon. We just did it a little bit too soon. We're going to use that in question 81 now that we know the speed. So we're going to say B, I should say. If I rearrange that, it ends up being equal to MV over Q times R. I got M, I got V, I got Q, I got R. Solve for the magnetic field. And what did that work out to be? We get 1.20 times 10 to the 1, which is the way they want it expressed, 1201. All right? Yep. Mm-hmm. That's a good question. That's a good question. On diploma exams, they used to on diploma exams require you to get one question correct and then answer the next question based on that answer. They don't do that anymore. So one answer will not depend upon the previous answer. That's good. Even though they had a system where they would have multiple possible answers for this. So basically, if you picked D, you would get a certain answer for 81, and it would get marked correct if your answer was consistent with that. But it still is bothersome to it. It's stressful to us, right? If one answer depends upon the previous, even if it doesn't really matter because they have multiple possible answers keyed correct, it's still stressful if that happens. They don't do that anymore, so you don't need to worry about that. I've still given you the questions because they're good questions, but you wouldn't see that scenario on the diploma exam. I don't think there's any like that. I don't think there is. But if that situation arose, I would, and I've just forgotten about it, then I would mark it the same way they used to mark the diploma exams. And that is, like if you got D, well, this is the answer you should get for 81, then a different answer, right? Make sense?